Good morning, everybody. You are gradually welcome to this morning's lecture, Chemistry 176. As scheduled, we are starting the lecture when it's exactly 9, please. As you come in, just like I wrote on the LMS platform, you sign in on the chat, indicating your name, your department, and your matric number. So thank you very much. We'll go systematically into this lecture. We will not rush ourselves. And I'm sure you will gain tremendously. Please get your jotters round and your notes and your writing materials along with you so that we can move on together. I wish us well in the program. Class, good morning. I think we should be happy to have this class, but I'm not too happy that I don't have enough of number of you when actually you are supposed to have linked up. You should be in class by now. I should have very close to 900, but I'm still, the number is not too encouraging. It's not too good, please. I don't know why it's like this. Please let it not repeat itself, that you people will be coming late. It's not too good. So please let it not repeat itself. I'm just trying to see if I can have more. It won't be nice you coming in between. Though I don't want to log you out, but at the same time, you must learn to be punctual at your lectures on time so that we can go far and that you will understand. If you come in between, it will not help your, if it not help your understanding. Then you will have seen on the chat that I've copied the YouTube link. So you can have it and utilize it as it's supposed to be. So well, wish you well. Okay, nice. Some people are giving information that they just finished the class, no problem. And that is why I'm holding on a little so that you will not be at loss. You will not be missing anything out of my lectures today. It's so nice you replied me. Thank you for that information that you just finished a lecture. And that is why most of you are just coming in. No problem about that. I wish you well in life. It's a matter of, it's just the season. When you concentrate now and you gain maximally, you can be sure that in the exams, you will also perform very successful. I wish you great success in life. God bless you. So straightforward, let us continue our lecture while we start that of today. I want to go a little bit backward, even though I know that I've introduced amines a little to you back so that we commence it fresh on the amines. The amines, the big name is amines that constitutes both the aliphatics and non-aliphatics that have amine as their amine as their functional group. So we can altogether say that the homologous series of compounds are the amines. And what are these alkanamides? They are derivatives of ammonia. You are very much used to ammonia. You can see my cursor there with NH3, ammonia there. And the derivatives of this ammonia, when we have the hydrogen of the ammonia being replaced by hydrocarbons, alkyl or aryl systems, then you have the amines. These are just few examples to show amines here. I have about 3 of them. You can see the relationship they have to ammonia. Ammonia NH3, you have either one of the hydrogen or 2 of the hydrogens or all the hydrogens in ammonia being replaced by alkyl groups, even though I'm making it the same methyl group replacing, it could many times it may not be methyl. And that is where the names of this one will come up from. Very soon we'll be going into trying to add to our knowledge on naming organic compounds. And specifically for these amines, we will be calling the alkyl or the hydrocarbon group and ending it with amine. So that gives us that one. So this is a methyl amine. This is a dimethyl amine, symmetrical. So we have 2 of it. Instead of saying methyl amine, we'd better call it as dimethyl amine. Same thing, this will be better referred to as a trimethyl amine. So, like I said, we'll be just breezing through, that is very briefly, we'll go through some nomenclatures, additional information on the general IUPAC method of naming organic compounds that are specific and unique for these alkanemins or amines. Then after that, we go to the next 3 bullets in that progression, checking on the properties and uses of these alkanemins, amines. Then we go into their preparations. Definitely each of them, each of these stages, I will be showing some equations, general equations mostly. And then those general equations, definitely in exam, will not be expected to work on general equations. We have some specifics. So we can always replace our general equation, maybe represented with AR or R, capital R, representing the alkyl group that is varying. So we check on the 3 aspect properties and uses stroke applications of the compounds. Then the second aspect will be how they are formed, that is their synthesis or rather preparations. Then we go into some reactions, which we depict the chemistry of amines. Very, very interesting functional group of homologous series of compounds. So on the nomenclature, the aliphatic forms of amines is the reason why we refer to them as alkanamides, giving the aliphatic aspects carrying the amine functional groups. Generally, okay, when I use amines now, I'm referring to both the aliphatic and non-aliphatic systems. Now, amines are a set of organic compounds that is central nitrogen bonded directly to carbon atoms. Those carbon atoms, they could even be aromatic many times, maybe some phenyl groups linked, some benzene rings linked to that. See, this because I gave initial or more of the hydrogens in ammonia is replaced by alkyl groups. Okay, thank you. Now you are hearing me. I'm no more muted. I've unmuted myself. Thank you. On chat. Okay. What will happen? Somebody is telling me I'm disconnected. That would be very bad. That would be very, 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 very bad. Well, it's nice you are giving me some fine chats. I can hear, we can hear you, Ma. We can hear you, Ma. That's good. You are reconnected already, Ma. That's good. So that means I'm on the line. That's why I stopped. This I can't hear you clearly. Are you sure, Sherifidin? Oyetunji? Please check your connection. People are telling me I'm connected back. So I think we can continue the lecture. I won't want anything that will disrupt you or disrupt myself. So I'm continuing. Yeah, thank you. I can hear that you can hear me. That's good. That's very good. That's very good. Very, very good. So, the examples I gave you the other time, let's not waste time on it. We have the methylamine with this one. You can see my cursor there. I've decided to make it this way in sharing my screen with you. Then the second one is the dimethylamine, and the third one is the trimethylamine. And all I've been saying, not to repeat myself too much, is that for the methylamine, you just have a methyl group replacing one of the hydrogen in the ammonia to give that formula up there. And for the dimethylamine, you have two methyl groups replacing two hydrogens in the ammonia to give our dimethylamine. And in the third aspect, we have three methyl groups replacing all the three hydrogens in the ammonia to give the trimethylamine. I will want us to look a little bit closely at the nomenclature as well as maybe the rule. You can see that when I was writing the names, I didn't leave any space in writing the detailed names. Then also the classification of the amines. Depending on how many hydrogens are on the nitrogen, which is the functional group there, we can classify our amine into four parts. We can have the primary amine, the secondary amine, the tertiary amine, and the quaternary amine. That's the 4th degree. I didn't put it here, but that is it. So what is germane, or the future of each of these amines? For the primary amine, you always have one alkyl group bonded to the nitrogen, and it is characterized by having an NH2 as its own functional group. While in the secondary amine, you have two alkyl groups bonded to the nitrogen, and it is characterized by NH functional group. The tertiary amine is characterized by just nitrogen with three alkyl groups bonded to that nitrogen. While for the quaternary, you have an N+, there is a positive sign on it showing the cation, and then usually you have the anionic side very close to that. We will talk more about that fourth one later on. Let's still concentrate on this primary, secondary, and tertiary amines. Very, very important, please, and germane to us that, okay, I still have some charts here. I love listening to your charts, but okay, they are all attendances. I'm too fast, okay. But I think I'm seeing some good information that I can hear you. Thank you, Sherifidin, that you can now hear me. I'm happy that you can hear me. That's good of you. Great. So I'll try to be a little, not too slow, but moderately moving on with you. So then, because namings are so important, though I don't want us to take too long time on the namings, may I quickly say that the common names of these amines is what I want us to consider at this time. Along with the general rules which we have or we are conversant with in naming organic compounds, for the amines, the alkyl group bonded to the nitrogen atom, peradventure, especially if there are more than one, must be listed or should be listed in alphabetical order. And finally, you end up with amine with no separation in the wordings. Then when you have the same alkyl groups repeated, maybe two of it or three are used, you indicate, you can use hyphens or prefixes like di or tri. So it will indicate which of them, of the substituents, are the same. And you just end up with a di whatever, then try whatever is there, and are bonded to the nitrogen in the amine. Let's look at these two examples, say 1 and 2 here, and use that to show what I've just stated here. In the formula, in the chemical formula for the amine in I, you have a CH3 on this bonded to nitrogen, and you have another ethyl, a C2H5 on the second, as the second alkyl. The two of them, ethyl starts with E, while methyl starts with M. So alphabetically, the ethyl should be mentioned first before the methyl. And that is the real name for this is better referred to as ethyl methyl amine. No spacings. You write the name straight like that. So check on the second one too. You have a methyl group, a propyl group, and also an ethyl group. So if comes first, followed by the M methyl, and then lastly the propyl. So it is better referred to as ethyl methyl propyl amine in that instance. Then there is a classwork I desire you take cognizance of. We have mentioned the classes of amines the other time. Right from the formula, what we should be able to identify these two examples we have spoken of. I've told you the characteristic feature when you have NH is referring to, and you have two alkyl groups, bonded directly to the nitrogen, then that is a secondary amine. So that means this first one here, I, is a secondary amine, while the second one that doesn't have any hydrogen bonded to the nitrogen and it has three alkyl groups bonded to the nitrogen, central nitrogen, we refer to that as our tertiary amine over there. So that's the class work we have to do over there. I'm happy it's just, it's people that are just streaming in. Can we get the first slide and this current one? Everything is in the YouTube. You have, hello, please check the first charts. The first chart gives you the link to the YouTube. So once you have the YouTube, you have everything. You don't need the slide again, please. Let's keep moving on in our lecture. So let me also talk on the systematic namings of our amines. Yes, you will surely have for the quaternary. I'll show you very soon. Yeah, that's okay. You will surely have for the quaternary. Don't worry. And that is Favor Ayeni. Yes, you will. Let's just move on and not disrupt the class further. I'm happy you are going on with me. So for the systematic naming of amines, the IUPAC system utilizes the suffix amine, which denotes the functional group. And when you have the longest chain, you ending with E, you remove that E and you replace it with AMINE, that is the amine. We will see an example to this, not really rules, but reminder of how to better systematically give the name of amines. So I'll take it up from beginning of the bullet again. The IUPAC system utilizes the suffix amine to denote the functional group, that is, it belongs to an amine, where the E ending the name of our parent hydrocarbon is replaced by AMINE. That is, you choose your parent hydrocarbon, the longest chain should be your parent hydrocarbon. The alkyl group with the longest hydrocarbon chain is our parent hydrocarbon. So you now use some numbers to indicate or identify the carbon where the nitrogen is really bonded to that parent hydrocarbon. Usually it has the lowest number. So that number appears before the name of that parent hydrocarbon or before the amine at times. Now the name of other alkyl groups that are bonded to the nitrogen functional group showing the amine is now preceded by italicized N, capital N, when you are typesetting, and you indicate that the group is on nitrogen. That is the other alkyl groups apart from the parent hydrocarbon over there. So let's see one or two examples in this perspective. Of course, the longest chain, well, this happens to be a primary amine because the classwork says identify the class. So since it's a primary amine, we only have one alkyl group. So the only alkyl group has maximum of 2 hydrogen. So that's an ethane moiety. Ethane moiety, you replace the E by AMINE. So that is an ethanamine. So that's how to name it straightforward, is a primary amine, like I said. Now look at the second one. Over here is also a primary amine, but the parent hydrocarbon has 4 carbon on it, and that's a butane moiety. So we remove the E of the butane and we replace it with the amine. So that is, and it's on carbon number 1 that is linked to the NH2. So that's a 1-butanamine, because it could be on other places. If I were you, I will ask myself, why didn't we say 1-ethanamine? Because the carbon are at the extremes. So wherever it is, it's always 1. So no need of putting 1 for the ethanamine, but it will be important to show it in the second example here. Now, let's look at this third one. It happens to be a secondary amine. On this nitrogen, the central functional group nitrogen, you have a methyl group bonded directly to the nitrogen, and you have a 3-carbon propyl group on the other side. Out of the 2 of them, the longest chain is the propyl. So the propyl becomes our, it becomes the parent hydrocarbon there, and straight off, it means it is a 1-propanamine. So on the N-nitrogen, which is ethylised, we have a methyl group. So that's better referred to as an N-methyl 1-propanamine. You can walk it through on your lecture notes that is near you and see some of this, even though you have the YouTube at your disposal with you. You can always have that. Let's check on this tertiary amine that has a methyl group linked to the nitrogen, small group, and a ethyl linked to that nitrogen, and also a propyl. Propane will be the parent hydrocarbon, so that will be a 1-propanamine. But on the N, ethylised, you have, and it has to be in alphabetical order. Ethyl will come before methyl, so we have an N-ethyl, N-methyl 1-propanamine. That will be the best way of referring to this amine compound over there. So with this understanding, I'm sure you are now used to the IUPAC system of naming amines. So for all substituents in the molecule, either it's on nitrogen or on the parent hydrocarbon, they must be listed in alphabetical order with a number or italicized N preceding where that substituent is. Let's look at one example just to summarize, or before we say a bye-bye to these aspects of the amine that we are considering. So numbering of the chain is such that gives each of them the lowest possible number. That is, gives the functional group the lowest possible number. So look at this compound here. It's also, what kind of amine is it? It has an NH. Well, if you are saying it's secondary amine, well, you say you can't see the link to the YouTube. I don't know. I've given you earlier. I will try and maybe at the end, try to see if I'll copy it again for you. Let's leave that aspect, please, and move on to continue with our lectures. So look at this compound here. Yes, that will be a secondary amine. That's good of you. So we have a methyl group. We have these butane derivative with a chloro substituent on carbon number 3. So a chloro substituent on carbon number 3, it is joined to the nitrogen on carbon number 1. So it's a 1-butanamine. It's a 3-chloro, that's one. Then on the nitrogen, you have a methyl ethylised. So on alphabetical basis, we have a 3-chloro N-methyl 1-butanamine. So that will now be what we have that is depicted therein. So, like the gentle person was asking, can we have example of a quaternary amine? I'm going to show it now. Like I said, it carries an N+ all the time. That is, after you've gotten, you can recollect your tertiary amine with 3 alkyl groups. Then when we now have a fourth one coming on nitrogen, you remember nitrogen from our elementary chemistry at O level, we know it's having a it's in group 5. Is a group 5 compound or elements rather, is a group 5 elements. And then when it surpasses the 3, the fourth one, we make it have a positive. That's the perspective. I can explain it to you, but that is where the quaternary is coming up, and is an ionized system. Now, this set of nitrogen compounds usually have 4 alkyl groups bonded to the nitrogen, like I said when I was explaining arbitrarily. So hence we refer to it as quaternary ammonium salts, since we are comparing amines with ammonia, NH3. You know, by the time you have, it's like, it is the derivative of NH4 plus, where the tertiary amine has all the H3 in ammonia replaced. So for the ammonium ion NH4 plus, all the 4 are replaced by the alkyl 2. So you see it from that perspective, and we refer to that as quaternary ammonium salts. Now let's go briefly into naming them too. The name is such that the alkyl groups are given in alphabetical order, which you are used to. And then lastly, you end the word with ammonium, all solidly in a single word. You don't separate them, just like amine, like we did. But since it is a positive moiety, like say cation, usually there is a counter ion near it, that is an accompanying anion is very close to it. So you name that anion after the whole solid word that is there. Look at this one, derivative of ammonium anion in NH4 plus, where we have all the 4 hydrogens replaced by methyl. That is a tetramethyl ammonium. Now the counter ion, which is the accompanying anion, is an hydroxy group. So we end the name in space and then hydroxide. So this compound is actually tetramethyl ammonium hydroxide. Look at the example below it. Over here, it's also a quaternary ammonium salt, where you have a propyl, 2 methyl groups, and then an ethyl, which makes the 4 alkyl groups that are bonded to the ammonium nitrogen, the quaternary nitrogen that is here. So in that wise, the accompanying anion here, or the counter ion, is a chloride. So naming it alphabetically too, we have E for ethyl, M for methyl, P for propyl. So that goes for the methyl is a di. So we have ethyl, dimethyl, propyl, ammonium, all solidly as a single word, no separation of the, no separation in between, and ending after a space with the chloride. So that is ethyl, dimethyl, propyl, ammonium chloride. That is how it is better referred to over there. Yes, our syllabus says akanamine, and in bracket amines. So it's nice you know that the amines encompasses both the aliphatic amines and the non-aliphatics, especially these aromatic amines. When you talk of aromatic amines, they have this phenyl moiety inside of them. The simplest of these aromatic amine is what trivially we refer to as aniline, and it is known as phenylamine. This is the structure here. You have the benzene ring with your amine functional group, a primary amine NH2, directly bonded to the benzene ring. So that gives it the phenylamine, which is our aniline therein. So it's the simplest aromatic amine that we have. The other simple compounds are named as derivatives of this phenylamine. For instance, you have the toluidines. What are the toluidines? We have the methyl derivatives of our aniline, phenylamines, even therein. And usually, because we come to the chemistry, we see that amines are bases. The NH2 make them rich organic bases. In fact, the most abundant organic bases, if you are asked in interview, you should be able to say immediately that these are amines. Amines are very good example of organic bases. I know you know of organic acids. So organic acid, this carboxylic acid are very good examples of those ones, and some other derivatives of these ones too. So for the methylamines, so the methyl anilines, that is methylphenylene, are amines. They are referred to as toluidines. Since they are basic, the NH2 is basic in that in phenyl means it directs to the ortho and para positions. So you can have the ortho and or the para toluidines, over there. And I'll show you the structure, at least one of them. You have, that's it, toluidines. This is giving us the para toluidine. When it is on position 2, either here or here, that is the CH3, if it's here or here, then we refer to that as a 2-methylphenylamine or the ortho toluidine. I'm sorry I didn't show it there, but that is just what it means to have that. Then we can also have other derivatives, like in our phenylamine, which is our primary amine. You can have the secondary form where you have, out of the NH2, one of the hydrogens is replaced by a methyl group and is referred to, that is, it's on N italicized. So you have an N-methyl aniline or N-methylphenylamine. That is this structure here. And that is what you have there. That's your, I think, yes, that is it. Instead of what you have on the phenylamine with NH2, one of the hydrogens is being substituted by a methyl group. So it's on the N that we have a methyl group, referred to as N-methylphenylamine. If we have all the 2 hydrogens on the aniline of phenylamine replaced by methyl, then we could have said an NN dimethylphenylamine, which is a tertiary amine, aromatic amine, that wise. So the name, you should not be confused at all. It's just like that. Even this last one is a secondary amine, where one of the hydrogens in the aniline is being replaced by a phenyl moiety. So showing that the NH, which is characteristic feature of any secondary amine, is having phenyl group at those 2 positions. So you will refer to as a diphenyl amine in that perspective. I don't think it's important you say NN phenyl and NN diphenyl amine. Just that one is okay. That is also acceptable. Now we check on briefly the properties, applications, and uses of these amines. Simple aliphatic amines are canamines. Those lower weight ones are usually gases, and they are characterized with ammonia smell. When you draw close to them, or they are close to your nostrils, they have ammonia smell in them as part of the property. For the moderately higher amines, they are having a kind of fishy odor, and they are liquids in their states. Then the higher molecular weight amines are solid in nature. Since amines are polar compounds, apart from the ammonium compounds, that is the NH4 plus derivatives, amines are capable of forming intermolecular hydrogen bonding, and you can see that intermolecular hydrogen bonding with each other, especially those that have hydrogen. And when they undergo, there is this hydrogen bonding in there, it affects some of their physical properties. For instance, their boiling points becomes higher because kind of dimerization occurring. You remember that's one of the, though we still touch it when we come to canoic acid, so carboxylic acid generally. Wherever group of organic compounds that have intermolecular hydrogen bondings are characterized by having slightly higher boiling points compared with their hydrocarbon counterpart that have relatively similar molecular weights with each other. So since they are polar compounds apart from the ammonium compounds that are, I won't say super saturated, that have the plus, it means generally are capable of linking up, exhibiting hydrogen bonds within them. This yields or is responsible for the increase in their boiling points compared with their counterparts having similar molecular weights that don't have any polar functional group inside of them. Then the same thing too, the boiling point of isomeric amines, especially when you have branchings in these amines. Branching in primary amines, let me read that last bullet. Boiling point of isomeric amines decreases from primary amine to secondary amines. That is what we are saying. That's why I place these important things in red, that volatility is enhanced by branching. So the more the branching, the lower the boiling points. Even though they have the same molecular weights, when you notice one is not branch, another one, isomer of it is branch. The one I know Professor Shonibari has taught you so much about isomers. So the isomers of these amines shows or proves that the one that is branch, we have slightly lower boiling point compared to same amine with molecular, in terms of having same molecular weight, that branching is not indicated or is not shown therein. Still on properties, applications, and uses of amines. They are quite abundant in nature. In fact, they are very significant in some special compounds like our amino acids. We have these amines there, our proteins, because you know amino acids are the building blocks of proteins. Our nucleic acids, we have these amines there, enzymes, coenzymes, vitamins, and some important drugs have these amines embedded in them. So they are quite applicable in this perspective, biological importance. Then it's nice you know about the hybridization aspect of nitrogen. You know, nitrogen is 14,7. If you show the electronic configuration, you will have the P3 singly occupied, and then you have the lone pair electron on the 2s2. If you show the electronic configuration, these are elementary things you are used to. The nitrogen in amine is sp3 hybridized. Its lone pair resides in an sp3 orbital, which I've just spoken of now when you show the electronic configuration. So amines invert at room temperatures through transition states, where their sp3 nitrogen becomes an sp2 nitrogen. That's in their inversion positions. Then back to their physical properties. We've talked about most of this, and that is the hydrogen bonding, that they exhibit hydrogen bonding. Apart from the ammonium ones, the all amines, they exhibit this, and that is what is responsible for even their high boiling points when you compare them with non-polar, and because of the polarity of that nitrogen, you know, that also indicates then the hydrogen bonding is also contributing to in this perspective too. And because of the polarity, the physical property, that is polarity of the nitrogen, you have it's been affecting its solubility also. Then these last points, you have some red denotations there, and I want you to take cognizance of that. You can write it in your lecture notes. The lone pair, because it's going to have, we're still going to use it to show some trends, especially in some of their reactions when we come to the chemistry of these amines. The lone pair electrons on nitrogen atom, like I said initially, when you write out the electronic configuration, you have the 2s2 there, responsible for the lone pair electron on nitrogen. It's what is responsible for amines being practical organic bases, and that is why they react as bases. And in the laboratory, in your 191 practical classes, that is, you are given some unknowns, you are asked to, and you still meet some of these two in your 376 practical, when you will be given some, or you may not be told that you have some amines among some unknowns. And by the time you pass through some reactions and you detect that this organic compound is somehow basic, you can very close to 100% be sure that that is an amine material bearing. The protocol or procedure for testing for organic bases will have been given to you. So now if it shows all positive activity, if it's positive to all those protocol that you are given, you can be sure that you can very close to 100% say that your material that you are given, though unknown, you are confirming that it's an organic base and it is an amine. So the lone pair electron on nitrogen atom is responsible for it reacting as bases and sharing that lone pair with a proton many times. And you have the protonation reactions. We are coming to some equations that will show this. Then availability of, it makes way for availability of electrons. And when you say a substance in organic chemistry has electrons in them, then you say it's a nucleophile, it's a nucleus-loving system because it is electron rich. So it means that electron rich, they are good nucleophiles, sharing the lone pair with an atom other than a proton. And we will see this in their chemistry. Already I've started the chemistry from that property. So let's see some few slides on how we can form or synthesize or prepare these amines. Though I didn't number it, we go into industrial formations or industrial sources of getting or preparing our amines. Then after that, we go to their preparation synthetically, and we'll be looking at these 5 germane methods of synthesizing amines. And I want you to take cognizance of their features. Like one is Hoffman degradation of amides. Amides are CONH, if you remember very well, where you have a carbonyl functional group directly bonded to an amine, NH kind. So that's an amide. Then how in the Hoffman degradation we can obtain our nitriles for that, our amines with that. Then we have reduction of our nitriles. Those ones give rise to very pretty number of amines too. From haloalkanes, I'll give you some equations, be ready to write some equations, and even though you have the G2, you can always turn there, and you have that. Then reductive amination of carbonyls. We see reductive amination of aldehydes and reductive amination of ketones, and show us some important features here. I'm taking time to explain because this is germane. We start picking them one by one. The last one will be synthesis of the aromatic amine, that is our aniline. And we see some general method of doing this quickly. So we pick on the industrial sources of amine because of the importance. Industrially, methylamines are obtained by passing methanol and ammonia over aluminum oxide catalyst in an inert supports at that very high temperature of 400 degrees C under high pressure. So you have your methylamines really being formed by this method. We'll be going through. This is the equation that shows it. You have sequential formation of series of amines. You have the primary first formed in the presence of more methanol on the more methanol in the system, you have the secondary amine being formed, then you have it. So there can be a mixture of this one. So that is the equation that shows how methylamines are obtained from methanol and ammonia under those stringent conditions, which I've shown. The next one is from benzene, where you have nitration of the benzene reduced to. Okay, before I go to the next one, which is the nitration of benzene, it's suffice for me to say that among the series of methylamines that are formed, the dimethylamine is the most important. And this is because we use it in manufacturing other important systems like synthetic fiber solvents, unsymmetrical dimethyl hydrazones, and other industrially important compounds. Also, they are utilized as fuels in jets and rockets. But notwithstanding, what is important is that you start with ammonia in methanol under these conditions at high pressure, great temperature, and catalyzed by this aluminum oxide. You have series of methylamines that are formed in there. So for the benzene nitration, it's a reduction reaction. That is, after you have nitrated benzene, you reduce it to our aniline. Let's see the equation, and that is it there. Aniline is finally formed. So you nitrate. Anytime from your elementary chemistry, nitrating agent, very important nitrating agent is conc HNO3 in H2SO4. Yeah, that is it. And you have the nitro group being formed instantly, which goes by electrophilic substitution on the benzene ring to give the nitrobenzene, which gets reduced, and you have your aniline being formed over there. Now, for another method, industrially obtaining amine is, well, this is acanamide. These are aromatic amines that are formed there. Now, for the last one, when you start from chlorobenzene, you can have, under this condition, from chlorobenzene in ammonia, copper 1 oxide at high pressure, and that high temperature of 200 degrees C, you have your aniline being produced therein also. So that gives us some industrial ways of obtaining important amines therein. Now, for our synthetic methods of obtaining amines, please take cognizance, like I said, of what characterizes these reactions, and as well as are they the methodology, and also are they economical, or are they not economical? So it's very important to take note of this, especially the 5 synthetic methods to be touching. Let me check on the charts. Somebody is saying you can't hear me. You should. Everybody is hearing me. Please check your system or increase the volume. I think my voice is rising enough. Yes, somebody is saying, Moses is still asking, do we have access to these materials? Yes, check the YouTube. The YouTube is recording already. So you have that, please. Those of you just coming in, that would not be too good of you. We have gone far, but notwithstanding, next time, don't come late to class. So please, Fisayi or me, I hope you can now hear me, please. You should be able to hear me. Everybody should, please. So let's move on. For the first one there, the Hofmann degradation of amides. So you have your amides already. Degradation means there's a breakdown through the Hofmann degradation. Why is it Hofmann? Is the man that discovered that in this method, you warm your amide with bromine in conc alkali. You know what alkali are? These are group 1 hydroxides, sodium hydroxide, potassium hydroxide. So you warm that amide you are starting with in bromine, and conc alkali. And this is a very good method for obtaining our primary amines. So this is, like I told you initially, that I'll be giving general methods. We are here, I'm not specific, I'm just using R and all throughout. So in bromine, in conc, sodium hydroxide, and then you have the degradation of these amide to give our primary amine. It's a good method, like we said, for obtaining primary amines in, why do we say good? Because the yield is high, it gives good yield. These are important things you need to know for your, maybe you come back for your postgraduate work or even your project work in chemistry. You have to work on methods that good yields, maybe very close to 90%, 100%, then you say, yes, this reaction is giving a good yield of that product. So especially for the primary amines, the Hofmann degradation of amides functions in this perspective. And you will be able to see this with this vivid example. This is a primary amine. We are starting with acetamide. Acetamide is your ethanamide. Ethanamide, we saw it. You should be able to know what ethanamide is. And that's the 2-carbon system with the amide functional group. So definitely this one is being degraded to give the methylamine, which is a primary amine. If this were not to be ethanamide, it were propanamide, then you will expect that this one will be what? Ethylamine. Yes. So you should be able to give the information. The R is constant, coming to R. So if there is this one is an ethyl system here with methyl as our R, then at the time I have it as a propyl, you should be able to give it. So please, that I'm giving you just one example on the screen. Now I've given you another example just during the lecture. Exams too are just like examples, which I believe you should be able to reciprocate and give me the correct formulas or correct equations, even in exams when such are brought out. Now, like we said, when we were listing the methods we want to check on, for the other one, that is reduction of either nitriles or oximes. These two methods are reduction methods, and it involves reduction treatments of either your nitrile or your oxime using lithium aluminum hydride in diethyl ether. Remember last lecture we had this. So though alternatively, you can also use sodium in absolute alcohol. And then the reduction of these two systems yield our amines. Let's look at the example. Here you have the reduction of your nitrile, while the second one is the reduction of your oxime. So you should know the functional group of nitriles and also that of oximes. Oximes are, you have a carbon-carbon double bond, then the carbon-nitrogen double bond, then on the nitrogen single bond OH. That gives the oxime functional group. We still check on this when we come to the chemistry of carbonides over here. Then for the nitriles, carbon-nitrogen triple bond between them gives the nitrile. When this R happens to be an hydrogen, that is the simplest nitrile, and not really nitrile, that's hydrogen cyanide. And this one will yield methyl amine in it. Other nitriles will give higher amines in them. So for the oxime too, you reduce same condition, and then you have your primary amine being formed therein. So you have reduction of those two groups of compounds to give our amine. We are synthesizing our amine. That's our desire. Now, for number 3, we want to synthesize our amine from some alloalkanes. And from alloalkanes. And I want you to take cognizance, like I said initially, of features of this material. Over here, we are utilizing alloalkanes for synthesizing our amines. This is a good method, appropriate for obtaining, forming, or preparing higher alkyl amines. You can see that the off-one is for lower or smaller amines. So, but this method is germane for forming higher alkyl amines. And this is by reacting the haloalkane as starting material with excess alcoholic ammonia under pressure in sealed tubes. The rate of this reaction is becoming faster because is sequential formation of alkylamine. One alkylamine that is formed is even more reactive than the starting ammonia. We have alcoholic ammonia. This is our haloalkane. Initially, you form your primary amine, which in the presence of more haloalkane, the primary amine enters a faster or less stringent condition to give the secondary amine. So, in other words, what I'm trying to prove what I'm trying to say therein is that the rate of reaction becomes faster when you start with alkylamine compared to the initial haloalkane and excess alcoholic ammonia that you are starting it with. So, as you form the amine, it enters into as a reactant. From the product becomes a reactant again, reacts with the haloalkane. Faster method of getting another amine, which is even secondary. And this one also reacting more haloalkane, you have that until you have your the quaternary being formed over there. Let me say that each of them can, sorry please, let me just pause myself for a minute. Thank you. We continue, please. Hence, in this reaction, the reaction is not generally convenient for preparing individual amines, since you can see that we have series of amines being formed. And more so in this system, each amine exists in equilibrium with their salts. That's another aspect which I want you to see, the formation of the quaternary ammonium salts. Though I'm not showing for all of them, I only showed for primary, forming the quaternary ammonium salts. Each of them can enter this R2NH, can also form the quaternary ammonium salts of it. Same thing, this one. So, in other words, this is part of, even though we are talking of synthesis of amine, we are preparing them, but this is an aspect of how amines react. Sorry, they are interwoven one way or the other. We are on synthesis now. We come to reactions deeper later, but already we have touched one aspect, formation of quaternary ammonium salts, from that last aspect, this one over here. Now, the fourth method is by reductive amination of our carbonyls. Here we are referring to either aldehydes or our ketones. And you will see them there. And you have for reductive amination of our aldehyde, that's your ammonia, in reductive amination, utilizing those reagents, ammonia over nickel chromium catalyst at quite high temperature. This method can be used to successfully prepare or synthesize appropriate amines, even from benzaldehyde, which is aromatic. So to say, we want to generalize using alkanals, ketones, and then we have benzaldehyde too, which is an aromatic form of it. Still, we are generating our amine, all of them being primary amine in this perspective. So the reagent is constant, is a reductive system, amination of them under reducing condition. So the amination, I'm repeating because these are germane, and though I'm giving general forms now, but definitely in exam, you can't have general forms. It's how you lay your bed, you have it. If a methyl is there, you just place methyl finally, when either you have to provide this or provide the final product in this amination, reductive amination of these carbonyls. So whether it's aromatic or the alkyl forms, aliphatic systems of our carbonyls, that is, you know the difference between ketone. We are still coming there when we come to carbonyls. All the time, aldehydes are terminal, while ketones, carbonyls are never terminal. So the carbonyls in aldehydes always have number 1 in them. So sorry, I'm going too slowly, but I think it depicts it because I've not taught you carbonyls hearing. Well, since the YouTube is there, I think what you are saying, endurance, no problem. You are welcome. That's okay. So we leave your, I've seen your chats. So thank you. Let's go to the last aspect or the 5th aspect, which is synthesizing our amine. Still synthesizing our amines. This time around, we are concentrating on our aromatic amines. I put a red there, sorry, because the alkanamines was what we are budgeting for, but we can't really study them without also referring to some aromatic systems, especially this aniline that happens to be the simplest aromatic amine in our studies. So from the reduction of nitrobenzene, utilizing tin and conc HCl, though this is not too cheap because of the tin we are utilizing. But let me read through so that you get it once and for all. Our desire is to form amine. So the method here is going to make us to obtain aniline. So, and it's we are starting from nitrobenzene, getting reduced, utilizing tin in conc HCl. And the tin is such that is added little at a time under refluxing. Refluxing means you are cooking over and over, just like beans, cover it, it steams up, it condenses, water condenses, come back again, like that. That's what we call refluxing. So our tin 2 chloride is formed in this process, and that is, the tin 2 chloride is now our reducing agent that oxidizes the material that is being oxidized. Sorry, the tin 2 is our principal reducing agent, itself being oxidized to tin 4, and it is what forms the complex acid with our HCl that we have used initially, and combines this with the phenylamine that is formed. So the targeted aniline we want to form is liberated from the double salt on treatment with the conc alkali, sodium hydroxide. This requires quite large amounts of our alkali to form the oxidized tin 4 hydroxide that precipitates out and dissolves as hexahydroxostannate 4 ions when the solution is strongly alkaline, after which our desired aniline is extracted by steam distillation. I'll show you the equation very soon. But like I said, it is not an economical way of producing our aniline because tin is an expensive material substance. Instead, economically, instead of the tin, we make use of iron turnings, which is quite cheaper in that perspective. So you have this equation depicting the synthesis of phenylamine, which I've just read out to us, or rather, which I've just explained out. You have the tin 2 being our main reducing agent, reducing our starting material, which is our nitrobenzene, to that aniline we desire. And then this is obtained, like we said, by, it is obtained and precipitated out by this large amount of sodium hydroxide. You dissolve what is formed, which is strongly alkaline, and you extract it by steam distillation. So, not to keep repeating ourselves, that gives us, the equation depicts everything here. Now, the last aspect will be on some of the important reactions of this amine. I've touched some before, and you can expect the general, anything that is an organic base, because we have said amines are important organic bases. I said it initially that they have lone pairs of electron, which we have easily proved out from the electronic configuration, and they are good nucleophiles, nucleus lovers, because they are electron rich. And these are depicted by some of these reactions I will start showing us over here. Now, amines are the most common organic bases. We have said that they are electron rich and their functional group shows that. So the alkanamines are much stronger, and the equation below shows that they are stronger Lewis bases because of their ability to donate electron pairs, which are on their nitrogen, to protons that are around. And you can see that from this water, you have the proton coming up and forming that quaternary form, and then the lone pair of electron on the nitrogen is being utilized in that perspective. Even the ammonium form too, what you know of ammonia when it dissolves in water, that is it over there. So for our amine is equally the same, and you can see his basic property being depicted by that general equation. So they are much stronger Lewis bases, because of those properties. The basic strength of amine is determined by two important factors, which I'm giving in my next slide, or summarizing. This we have said earlier, that there is availability of electron pairs which can easily be donated to a proton, and that's why they are good nucleophiles, electron rich themselves. The second one is a factor, is that the ease at which protonated amines do undergo solvation with water molecules is high, because it's at ease. This one is, so to say, they are said to be stabilized. Then in terms of strengths, please, I want you to write it down, and that's why I'm putting it in red too. We will keep seeing some of these important things. I try to high mark some, not everything, in red, just to show you features that you need to work on, or you need to know on these reactions of amine. The release of electron pairs, since we said they are good nucleophiles, they have electron pairs, so which they release or donate in the course of their reactions. So the release of electron pairs for donation is determined or supported by electron donating effects. And this is not far-fetched from our inductive effects. When you have a key group, we talked a little bit about SN1 and SN2 reactions on Tuesday, where you have primary, secondary, and tertiary carbonium ion, when we said the carbonium ion is stabilized in the tertiary form. That is, there is higher inductive effects, more release, more nucleophilic. The same thing too, not just carbonium ion. Now for nitrogen. When you have in the tertiary amines, where you have 3 alkyl groups, they make that lone pair electron more accessible, more nucleophilic, more electron rich. So that is why they are, in terms of basic strength, the tertiary amine is the highest. So as you move away from tertiary amine, there is decreasing trend in the basic characteristic. And that is easily explained, or that is what I've just explained to you, because the nitrogen here is sandwiched by alkyl groups that are pushing electron to the nitrogen. So that's why it is the most basic among them all. And the trend goes from tertiary, decreasing trend goes from tertiary to secondary to primary, and then to ammonia itself. Let's just read through the slides. It's a matter of common sense. Just look into it from that perspective, and you get what I'm trying to say in these aspects. I have some charts. I don't know. It's okay now. This one we can't see the slide you are talking about. Okay, it's now okay. That's good. I'm happy you have solved your problem. That's okay. That's okay. That's okay. Thank you. It's attendance they are giving me. No problem. So we move on. Now, continuing with the chemistry and reactions of these amines. Since solvation is made easier and favored by hydrogen bonding between the amines hydrogen atom, or that is the one on the nitrogen, and oxygen atom of the water, which is solvating it, we expect that the following ease of solvation of protonation of amines will decrease in the following trend. Please take note. For solvation, it is the opposite way around. The ease of solvation of protonated amines decreases in the following trend. From ammonia to primary to secondary amine to tertiary amine. Now, those two factors, or those two we have considered, and we have put our common sense to understand them. Combining the two of them now, that is electron pair donation and ease of solvation, it now boils down to give us information on the basic strength, and that is why I'm putting notes in red here. Please put the notes 2 down in your notes. Basic strength of amines will therefore increase in the following order. Can you see? Secondary, because it has at least 1 hydrogen in it, more than that of primary, and then tertiary before the ammonia. So basic strength of amines can be modified by different electron donating inductive power or donation of different or various alkyl groups. We can't do without considering bulkiness here, and that's where the steric hindrance of bulky groups may have effects, and have effects in the impairing reactivity despite favorable electronic effects in this perspective. So we still read through, and we now see specific reactions. After this slide, we see specific reactions of these amines therein. What we have been talking about is a summary that aliphatic amines are quite stronger bases than what we said they are derived from, that is ammonia. For the aromatic amine, aniline is a much weaker base than ammonia. And well, quickly, let me explain this. The positive charge acquired on protonating is widely distributed among the alkyl groups of when it's an aliphatic amine. But when it is aniline, for instance, unlike an aniline that has its charge localized in the region only of the nitrogen atom, and it is not distributed in the ring. So in this way, negative charge possessed by phenoxide anion does. So if you look at it from now your NH2 directly bonded to a carbon on the aromatic phenyl ring, we now have it activating the auto and para positions. Now, introduction of a nucleophilic substituent, say a nucleophilic substituent like hydroxyl or methoxy group, CH3O, is being introduced to the ring of aniline, phenylamine, that's what. Now, especially at position 4, this can increase its basic character since it causes an increase in the electron density about the ring. So the effect is transmitted to the amino group, making the lone pair electrons on the nitrogen atom richer in electron, more nucleophilic, hence making the aniline derivative more basic. That is depending on whether you have a ring activating substituent like hydroxyl or methoxy group on all those position, like position 4 and 2, that's a ring activating. Also, protonation of the amino group on phenylamine has significant effect on its directing powers, especially in a strongly acidic medium. And that will be seen in your 191 practical, when I pray there are chemicals to show some of these reactions that we are talking about. So it leaves only the inductive effect operating. So for electrophilic substitution, the cation now directs predominantly to the 3 position owing to the deactivation of the ring. So that is why that is happening there. So on reactions now, we will look at it from this 6 perspective, and I want you to take cognizance of that over there. I will still indulge you I want you all to still be on until we finish the classes, please. I can see some people wandering off. Don't wander away, or else your reaccreditation will not be accepted at the end of the lecture. So, based on, like we did for formation and preparation, looked at the industrial sources of obtaining amines, and also we looked at some synthetic methods of preparing amines. In these reactions of amines too, we want to see their salt formation with practical example, acylation amide formation from amines, and this also involves carboxylic acid. So when we come to carboxylic acid, we still touch this aspect too, please. Then carbylamine tests, which is a very germane test we use in identifying amines. It's a reaction of amines where you have foul odor being displayed. The whole lab will be smelling in a very foul way. Just when you are doing qualitative tests to determine whether an amine is there, testing for a primary amine. Then formation from the amine, we want to see how we can form quaternary ammonium salts. Then their reaction with nitrous acid, very interesting to get a number of series of homologous series of compounds on saturated, and so on and so forth. So then we come to diazotization, which is also germane in our chemistry 191 practical, which is an applied aspect of this course. For the salt formation aspects, formation of stable crystalline salts utilizing mineral acid from both aliphatic amines and aromatic amines like aniline. Can you see? So we have these primary amine, methylamine, along with mineral acid HCl here. You have the formation of these salts. That is the ammonium salts that is being formed here. This is also a primary amine, the methylamine, in the presence of our H2SO4. That's the mineral acid here to form that one. This is an aromatic, the aniline, amine. And then we have the salt before. So for this is better stored in form of phenylammonium chloride, this form, since this rapidly deteriorates on exposure to light. So formation of these salts, a good way of applying it is in storage of anilines. Anilines will be better stored in the salt form, in the phenylammonium chloride form. Then you can easily generate your aniline back when you need it by mere treating the salt in excess sodium hydroxide. You generate your aniline back. So we want to learn how salt is being formed, and also the usefulness of that salt is used in keeping our aniline in good shape until we really need it. Here we just add sodium hydroxide and we recover back our aniline. So generally, addition of aqueous alkali to salts of amines will liberate that amine. And that's a major reaction to your 191 practical. You form the salts of your amine, and then you generate back your amine by adding aqueous alkali. You are able to generate back your amine in that aspect. The second aspect is in the reaction of amine is the acylation. You know the acyl group. Acyl groups are RCOX, or rather, let me just say RCOs, where you have R bonded to a carbonyl moiety. Carbonyl moiety. This is also, you have also an acyl group in anhydrides. This is an anhydride that is here. So reaction is for amines that have replaceable hydrogen here. You can see a primary amine, RNH2, and also this aromatic primary amine to aniline that is here. So reactions for amines that have replaceable hydrogens, aliphatic and whether is aryl amines, primary and secondary amines are readily acylated in the cold by acyl halides or acid anhydrides to form the corresponding amides. I told you before, amides are CONH, or you say NHCO, whichever is an amide. So we are forming from amine, we are going to amide. That is the aspect I was saying we will be touching under amides. There are also good derivatives of amine, the amide formations there. So like this one with aniline specific one, the amide form of that one is known as the N-phenyl alkanamide, which is the alka there refers to the R. So depending on what is the structure or the nature of our R that is depicted there, that is there. No problem. I'm seeing, I check your charts intermittently, and it's okay. It's okay. They are just attendances, and that's it. Okay. Somebody is trying to raise up the hand. What do you want? Can you write your information down if you are raising up your hand? If attendances are not taken, won't you come in? Please don't disturb the class with raising up a hand on attendance, please. So if you like, be there, you are doing yourself. So we move on with what we are out to achieve. That is forming our amide from our amine in this. Okay, Eyo, you are raising hand. What do you want me to do, Eyo? Eyo. Don't disturb my class. Oh. I don't know where you are so that I will unmute you, but you can write your comment down, Eyo. Write your comment down if you feel it's an important comment and it will make our lectures to go on fine. Or else, maybe after, I will unmute you and you will talk to every one of us. So let's just move on, please, at least for now, please. So that is amide formation from our amine. Yeah, the Kabila-Amine test for primary amines. It's a very important test we use in our practicals in 191 and generally not just 191 for saying qualitatively, we are saying that this is an amine, especially when you are not sure this is a compound. So on warming aliphatic or aromatic primary amines in chloroform and adding few drops of alcoholic alkali, you will perceive pleasant foul odor. This confirms the presence of isocyanide, or what we refer to as the Kabila-Amine isonitride has been formed, and that is it. RNC has been formed in chloroform with your conca-alkali, this time KOH. Now the test is able to tell us or distinguish that is this a primary amine from other classes of amine, but the sensitivity depends upon volatility of our isocyanide that is being produced in that reaction. So you can see it, that's the reaction I'm placing there. You have your amine, chloroform, and then you have your potassium hydroxide, which is your alcoholic alkali. So to form that alkyl isocyanide, which has the foul odor and gives that wise. So, well, it's just an advice that each of the generals have given you. Will you try and place some good things there, maybe, and try to see if you can work out equations. You complete the equation in each of the cases, trying to replace your R with methyl, ethyl, propyl. These are simple alkyl groups that you can easily work on and use in mastering these reactions, preparations that we have talked about under amines. Now, how do we form our quaternary ammonium salts? We have talked so well about what quaternary ammonium salts are. I said it under nomenclature. We have been touching it one way or the other too in the process of our lecture this morning. Let me say straight off that presence of excess haloalkanes produce high yields of quaternary ammonium salts from your amine. Just place so much or very great amount of our haloalkane, and you have your quaternary ammonium salts being produced. The reaction is a progressive substitution of hydrogens, like in ammonia, to form complex mixtures, to form mixtures of either your primary, secondary, or tertiary amines, or on the nitrogen atom of the amine by key groups, usually a methyl. That is, what we are doing is a kind of exhaustive methylation, step by step, until you finally exhaust it. Recall synthesis of amine. When we were there, we did something like this, exhaustive methylation, when we have the ammonia reacting with haloalkane to first form primary alkane, and we saw that it's a faster, the progression of reaction is even faster when the primary alkane acts at our starting material to get the, so you have a mixture of the amines that were formed in that perspective. So we are bringing it here too. The process here is also called exhaustive methylation of our synthesized amine to form the quaternary ammonium salts finally. So also quaternary ammonium salts can be formed by heating tertiary amines with excess of the appropriate haloalkane. So reaction with the haloalkane is what is germane here. Over here we have iodomethane as our haloalkane in this reaction to give tetramethyl ammonium, then the counter ion, which is the iodide over there. That is the anion. We have the iodide. Don't forget the naming we did that time. That was what we did, only the nomenclature. So what is the implication of the heat here? The heat is trying to help us overcome the steric crowding that is in this tertiary amine, so that the reaction can come up. So we have seen it the other time, and that is it, that we are forming our quaternary ammonium salts. That's it, quaternary ammonium salts. Finally, so you have the haloalkanes systematically still being added. First of all, alcoholic ammonia, more stringent. Then that's why we call it successive methylation. Successive methylation. If it's because we are making use of iodomethane, methyl iodide in our, so that's why we call it a successive methylation, exhaustive methylation therein. So we have that one. And then another one will have been the reaction of our amines with nitrous acid. This is also germane and very important to get a number of constituents. Very soon we check it on the next slide. But what is happening here is that freshly prepared nitrous acid, HONO, or better still, you can put it as HNO2, reacts with our amine to give the diazonium moiety that is here, where my cursor is, a dehydration reaction too, and we have the liberation of nitrogen from the diazonium moiety, giving the carbonium moiety, that is the R+. Now, the nitrous acid here is always generated fresh every time the reaction is supposed to be used because it's not too stable. So from dilute H2SO4 or HCl as acid on sodium nitrite, you can have that nitrous acid being generated. So the product depends now on the type of amine that you have started with, and then the conditions under which the reaction is being carried out. The aliphatic primary amine always give off nitrogen at that stage, so that you have the unstable alkyl diazonium ion that is being formed, which decomposes. So the decomposition now is what now gives rise to a series of reactions of the carbocation R+, which I'm going to show you those series of reactions of the carbocation. What is happening? Okay, people are streaming in. That's not a problem at all. If you are streaming in, just stay there. You are streaming in, stay there, but don't disturb others. That's the most important thing. I'm not seeing anything too germane here. Nothing more than that. You are just streaming in. Let's just keep listening to it, to the lecture as we move on. It's okay. I know our 2 hours will soon finish, but let's go a little far today so that we finish up these amines and then we'll be able to know we are going far. Now, upon our the subsequent reactions that occur on the carbocation that is formed, let's see these examples. For instance, it can take up, it can be hydrated, it can take up water and form the alcohol. Examples of amine reactions with our nitrous acid, resulting into formation of varieties of products. Now, in the formation of our alcohols, what happened? After it has given off this N2, you have the carbocation, which undergoes the reaction we want. In your 191, you are going to demonstrate this reaction. And when you hydrate it, you add water, you have formation of your alcohol. Over here, because the carbocation is a methyl ion, so then it is methanol that is being formed. Now, if you have the alcohol reacting with the carbocation, you have the formation of our ether. I think we mentioned this too last time. Ether is formed from reaction of these above methanol and other methyl carbocation that are formed there will now be able to result, giving us the ether. The carbocation, depending on the structure, we say something like that depending, product depends on the type of amine that we are started with and the conditions of the reaction. So we are looking at the conditions as well as the nature of the amine we started with. If the nature is such that you have the carbocation in this form, the alkene is formed from loss of proton from the appropriate carbocation. So there is loss of proton, removal of H+. So for ethylamine and other higher primary alkene amines, amount of ether formed is quite small, and it is usually obtained together with certain amount of alkene. You have unsaturation being introduced from loss of proton from that carbocation. So loss of proton from this will result in the unsaturated alkene derivative of the amine we have started with over there. Also on the carbocation, you can nitrate it. Presence of an NO2 plus ion will result in the nitroalkane. So the nitroalkane is formed from direct reaction between that carbocation and our nitrite ion that is in the medium. The amount of nitroalkane formed increases as the yield of alcohol falls off. Then the carbocation in the presence of an acid, when hydrogen acid is used, we have small quantities of the haloalkanes also being formed. So depending on what the X is, Cl minus there give RCl. So the use of aromatic primary amines on our nitrous acid will yield more stable diazonium cation than the aliphatic that we have here. This is part of the practicals you will be demonstrating on in your 191 practical on full resumption. So I'm asking you to check up details of this reaction using the secondary amines and aliphatic tertiary amines for that one. We are gradually moving to the end of our lecture this morning. Let me touch these aspects, or rather say few things more, that diazotization, the coupling reaction, which we have studied above, you should be able to show them with appropriate equations, and the implications I've explained, which I want you to take cognizance of, that is, of that aspect with the nitrous acid. I'm seeing some reactions here. Okay, direct message, no problem. If it is a direct message to me, I'm not seeing anything more than attendance over here. All these are all attendances. I'm trying to see if there is a hand that is raised. Okay. 2 participants raising hands. Let me see. I won't want you to make noise, but I will unmute you if you make noise. Let me quickly have your reactions one by one. If you can, if Babatunde is there, he should be the only one that's, well, let me not embark on that. He should be the only one that should talk. But if the noise is too much, I will just unmute yourself if you raise up your hand now. Hello?
Hello, ma.
Yes, please.
This
You have the floor. Talk.
This is Sherifdin Coyote.
Yes.
Please, ma, my phone is almost dead, and I don't know that. I don't think whether I will follow you to the end of the class.
I'm
Please,
even rounding up now. We have tried. We have tried. We are almost 2 hours. We have used more than 1.5. That's okay. So any moment from now, we have, but get the YouTube. Yes, please.
Okay, I've already gotten the YouTube, ma.
Yes, the next person.
No,
only one person at a time.
Hello, ma. Yes, ma. I couldn't see the attendance sheet, ma.
Just write it on the chat. Yes, the next person.
Ma, data.
Okay, next person. We are rounding up for today. Hello, next person. Just unmute yourself, give your information, and mute yourself again. The next person, please.
Hello, ma. I've already gotten the link to the YouTube.
That's very good of you. Thank you.
Thank you,
please mute yourself back. Next person.
Hello, ma.
Yes, please.
Yeah, well, I've not seen the link for the YouTube.
It's on the chat, please.
I check my chat,
get it from your others. Don't worry. Or mute yourself and let me have another reaction.
Good morning, ma.
Yes, please. That person talk.
Please, how can we get the particular slide to this?
That's on the YouTube. It's because you've not been listening. Please mute yourself back. Any other cogent information? I know we have gone far this morning. Sorry, your data. Yes, please.
Ma, good morning. Yeah, please, the link to the attendance sheet. I couldn't sign for the last class.
Just put the chat, please. Put it on the chat.
Yeah.
Yes, the next person. Please mute yourself back immediately you finish asking your question.
Morning, ma.
Yes, please.
Could you explain the part in the beginning about the auto and para forms for toluidines?
Okay, I'll do that. Mute yourself. I'll do that just in a couple of minutes. Any other information? Unmute yourself before.
Ma.
Yes.
On page 77, you said each amine exists in equilibrium with their salt. What does that mean?
Each amine
exists in equilibrium with their salt.
I'm on 77 already. I'll go to the one that lady asked now. Immediately I finish answering you. Each amount, I don't know where.
That's line 6. Each amine exists in equilibrium with their
amine. Okay.
Yes, ma'am. Sorry,
each amine exists in equilibrium with what? Yeah. Hence, the reaction is not generally convenient for preparing individual amines. More so in this system, each amine exists in equilibrium with their salt. Yes. If you look at these, it's like exhaustive methylation. You start with alcoholic ammonia, you have your haloalkane. First of all, primary amine is being produced. This primary amine turns out to progressively even be faster in reacting with the haloalkane to get the secondary amine. So you have a mixture of amines. That's what we are. Then, even each of these amines is capable of forming their ammonium material. So that's what I mean when I said that each of them, where is the statement again? That each of them exists in equilibrium, even with their salts at the same time. What we are saying is that we cannot isolate a particular amine from here, because as you have the reaction progressing, the reacting haloalkane produce the primary alkane and primary amine, and then the primary amine enters again to react with more haloalkane to give maybe the secondary amine. Can you see it from that from this one?
No.
You should be able to see it.
Yes, ma'am.
That's it. It's because you are not opening your. I'm sharing my screen with you already. You have your alcoholic ammonia reacting with the haloalkane. This under we are producing amine from haloalkanes. What we are saying is that you cannot isolate RNH2 because immediately it is formed. It's either it goes into its salt or it even reacts with more haloalkane to form the secondary amine. Even the secondary amine can go to its salt and form. So you have series of amines and also series of salts of the amines that are there. It's a very simple sentence that I'm trying to do. A good method for synthesizing higher alkylamine, is that not what we said? By reacting haloalkanes with excess alcoholic ammonia under pressure in situ. The rate of this reaction becomes progressively quicker because the formed alkylamine are more reactive with more of the ammonia to form the next step, and so on and so forth. So generally, the reaction is not generally convenient for isolating a particular or individual amine. More so in this system, each amine is still able to be in equilibrium with their salt. Though with the salts, immediately you add your alkali, you result by getting back to amine. Is that not your 191 practical, which I just talked about? So that. Then the other lady was asking a very germane question about positions. The person was saying, when you pick like aniline now, once it's the monosubstituted material, the number 2 position are auto, the number 3 position are meta, and then number 4, one single 4 position is para. She was saying that for their derivative, are you talking of toluidine? That I said I didn't put the auto toluidine here, but I've put the para where you see my cursor. On position number 4, you have a methyl. On the aniline, this is the aniline, the aromatic thing, and it is ring activating. Both position 2 and 4 are ring activating. Can you ask that question again? The lady that asked, but I think I'm on it already. This is.
I asked which positions were the auto and the para, and when you know the differences.
The auto positions are position number 2. Is that okay? And the para is position number 4. You have done this at your elementary stage. Once you have a monosubstituted, hello, please. When you have a monosubstituted, hello, please, just keep quiet and mute yourself. When you have a monosubstituted, you have a benzene ring. NH2 is bonded to the benzene ring. So it's a monosubstituted benzene ring. Now, immediately it's monosubstituted, every other position can be numbered from that place. That place becomes number 1. Other places takes over. The next one there is 2. This is 2. This is also 2 this side. You can have 3 different positions once you have a monosubstitution on the benzene ring. The immediate carbons are position number 2s or auto position. The third position are also 2 of them. We call them the meta positions. And then the 4th position, which is the 3rd type, is the para, which is just 1 position. Though when you are numbering them over, if they are more than 2, that is, if you are going to have a second substituent, like in this toluidine, this is now a para, or number 4 toluidine, that is 4-methyl aniline. No. So it's quite straightforward. You can check on some other textbooks. So we have position 2, position 3, position 4. Whether you name it this side, this is also position 2, position 3, position 4. Though there are 6 actually on the benzene ring. But once it is monosubstituted, that is number one. And others you can number. Yes, please. Mute yourself. Please, when you are laughing or you are messing up, I will unmute everybody if that's the case. I need you to unmute yourself when you are asking serious questions. Like they have asked serious questions. I've explained now. Yes, please, go on.
Please, my chat here is blank. I can't see the link to the YouTube and the attendance sheet.
Get from your colleagues. I've placed it initially. That was the first thing. That means maybe you came late to class, but that is not a problem. Hello? Any other information?
Excuse me.
Yes, please. Take over and please ask quickly. I've answered all questions.
Okay. You mentioned the increasing strength of amines from 3rd degree to ammonia, but you didn't mention that of the 4th degree.
Number 4 position. You mean on this benzene ring that is monosubstituted?
No, the increasing strength of amine that you mentioned that.
Oh, very, very germane and important. That's on the reactions. Abi, when I was giving a kind of relativity in terms of comparing their nucleophilicity or their basicity. I'm not too sure. Is that what we said? Is that what you are saying? Hello? Is it this one's? This one I'm displaying? This one and also the next. Yes. It is this one. Yes. Yes. Decreasing trend in basic strength of amines from tertiary amine to secondary. Now, before I finish explaining this, let me say that our next class will be Tuesday. Tuesday in the morning, 9 to 10. I think we can still have it 2 hours if it's possible. But some people, if you know, let Babatunde contact me. If you know you have a lecture 10 to 11 on Tuesday, but it's on our timetable that we're supposed to meet 9 to 10. So be sure that you will have me 9 to 10 on Tuesday. Is that okay? And also on Thursdays like this, 9 to 11, 2 hours. Is that okay? So for next week, those 2 are germane. Then the other 2 extra times I placed. Please take cognizance of that. Who can remind me of the other 2 quickly, please? Just unmute yourself and give me.
Wednesday 4 to 5 and Friday 9 to 10.
Monday 4 to 5. Monday
Wednesday.
4 to 5 and Wednesday 9 to 10. That's good.
Wednesday 10 to 11. Wednesday 10 to 11. Okay.
Wednesday, yeah. Somebody was saying Wednesday 9 to 10 is not convenient. Then there's a physics fix that it is Wednesday 10 to 11. Do you all agree 10 to 11? Wednesday?
Yes, ma'am.
Yes, ma'am.
Okay, that's okay. And thank you for sending those texts. That's good. So please mute yourself back. Thank you very much for being here. So I'm happy